So hi all, today we will see the induction motor working. In the last class we have seen the constructional details of induction motor. So on completion of this period you could able to know how the induction motor will run and what principle. And induction motor on load and no load also we will see. Okay. Why does the rotor rotates? Okay. See, we know that there is a stator and also a rotor. Here if we observe, there is no connection between the stator and rotor. And an induction motor is a self-starting motor. How it will run and why it will run, we will see in detail. Okay. So here the reason why the rotor of an induction motor is set into rotation is as follows. Here, when the three-phase stator winding are fed by a three-phase supply, then a magnetic flux of constant magnitude, which is a rotating magnetic flux, okay, of constant magnitude, but rotating at synchronous speed is set up. So here, when we give supply to a stator, a three-phase supply, then a rotating magnetic field will set up in the rotor, that is rotating at a synchronous speed. So the flux which got set up at a stator will pass through the air gap and sweeps past the rotor surface and so cuts the rotor conductors, which as yet are stationary. Okay. The rotor is yet stationary and it is cutting the rotor is at stationary and the flux, the developed rotating flux is cutting the rotor conductors. Though it cut the rotor conductors, the rotor is at stationary. Okay. You have to clearly understand the concepts. Okay. So due to the relative speed between the rotating flux and the stationary rotor conductors, okay, an EMF is induced in the rotor according to the Faraday's laws of electromagnetic induction. So here in the rotor conductors, an EMF will be induced according to the Faraday's laws. So now in the rotor, an EMF is induced. So the frequency of the induced EMF is the same as the supply frequency. So here in the induction motor, the rotor frequency, the EMF frequency will be changing. Now when the rotor is at stationary position, at that time the frequency of the rotor EMF is same as that of a supply frequency, that is 50 Hertz. So its magnitude is proportional to the relative velocity between the flux and the conductors, and its direction is given by Fleming's right hand rule. The direction is given by the Fleming's right hand rule. So since the rotor bars or the conductors formed a closed circuit, so rotor current is produced as there is EMF and it has been short circuited with the end rings. The rotor bars are short circuited with the end rings. Hence, there will be flow of rotor current. Okay. So the rotor current is produced whose direction is given by Lenz's law. So the direction of the current is given by the Lenz's law and is in such a way as to oppose the very cause of producing it. So the direction will be produced in such a way that it will opposes the very cause of producing it. So why does the rotor current has been produced? See here, in this case, the cause which produces the rotor current is the relative velocity. So, only due to the relative velocity, the current has been produced. Relative velocity between the stator rotating magnetic field and the rotor which is at stationary. Okay, so the stator rotating magnetic field is rotating at synchronous speed and the rotor conductors are at stationary. So there is a relative velocity of speed is that is ns. Ns, the synchronous speed, that is stationary speed is stator is stationary. You should understand that. Okay, you should be very much clear. Stator is at stationary, but the magnetic flux, the rotating magnetic flux is rotating at synchronous speed. Okay, and the rotor is also at stationary now initial condition. So the rotor is at stationary and the magnetic field, rotating magnetic field is rotating at a synchronous speed. So there is a relative velocity between these two, the conductor and the magnetic flux. So only due to which the current has been produced, because due to this EMF produced, because as EMF produced, as it is a short circuited conductor, so hence the current produced. So the current direction will be in such a way that why it is produced, it will oppose it. It will opposes it. Okay. So in this case, the cause which produces the rotor current is the relative velocity between the rotating flux of the stator and the stationary rotor conductors. Hence, to reduce the relative velocity or relative speed, the rotor starts running in the same direction as that of the flux rotating. Okay. So, now it will start the rotor will start rotating. Because of the Lenz's law, it is rotating. Okay. So, in order to oppose it, the relative velocity in the same direction of the magnetic field, it will rotate and tries to catch the rotating flux, but cannot do so. So, it will try to catch the rotating magnetic field because, so if we observe, this is a stator, say, this is a rotor. Now rotor started rotating. Already stator magnetic flux is rotating. Okay. This is called, this R is representing for resultant. Okay. Or otherwise you can write it as a stator flux, pi s. Okay. So this is start rotating with the speed of ns. Now in R, the rotor started rotating. Okay. So the actual, why it is rotating only in order to reduce the relative motion. So it want to reduce the relative motion. So here what is the relative motion? That is ns minus nr. So the agenda is that it will try to the maximum that to catch up the synchronous speed or to get zero relative speed. But What happens at zero relative speed? Example, we will think that nr is equal to ns at this speed. Okay, so we know that Faraday's laws for inducing an EMF, the three main requirements are a conductor, a flux, and relative motion between these two. Okay, so when nr reaches to ns, synchronous speed, when rotor reaches to synchronous speed, then there will be no relative motion between the flux and the conductor. Hence, there will be no induced EMF. If there is no EMF, no current. Okay. So what this one I'm telling. Okay. See, the rotor tries to catch up the synchronous speed, but it cannot do so. Why? Because say if nr reaches to ns, then the relative motion is zero because the flux and the conductors are rotating at the same speed. Then EMF will be zero. EMF induced in the rotor will be zero. Then the current produced in the rotor conductors also zero. At this position, the rotor does not rotate because there is no factor which is allowing it to rotate. When current is also zero, voltage also zero, at that time what it will happen? It won't rotate. So what happens? It will slow down. So suddenly it cannot stop because already it is in running position. Okay. When it's slowing down, when the rotor is slowing down, again there will be a relative motion between the flux and the conductor. Okay. Hope you people are understanding my point. Okay. So when the rotor is slowing down, we observe again there will be difference between the ns and nr. Then there will be existence of E and I. So likewise, the rotor will never catch up the ns. Okay. So here, the setting up of the torque for rotating the rotor is explained below. So in figure 1, we will see the stator field which is assumed to be rotating clockwise shown downwards, and the relative motion of the rotor with respective to stator is anti-clockwise. And by applying right hand rule, the direction of the induced EMF in the stator is found to be upwards. Okay, this is the figure A, B, C, figure 1. So here, say this is a stator, the flux is rotating in this direction, the flux is linking here. Okay, it is assumed like this. So the direction of the flux due to rotor current alone. So in this figure, only due to the rotor current, the direction of the flux only due to the rotor current is in this direction. So the relative motion is anti-clockwise direction. But now by applying the left hand rule and by the effect of combined fields, that is stator field and also the rotor field, it is clear that the rotor conductors experiences a force tending to rotate them in a clockwise direction. So here if we observe, this is a flux which are linking to the rotor and this is the direction of the flux at the rotor, and this is a stator field. So both fields are tending the rotor to rotate in a clockwise direction. Hence, the rotor is set into the rotation in the same direction as the stator flux. So this is what it has been, the direction has been given with the left hand rule. Okay. But according to the Lenz law, directly we can, because both the rules can be applied here. Okay. By both the rules, you can understand this concept. Slip. So what is the slip? In practice, the rotor never succeeds catching up with the synchronous speed. Yes. In practice, the rotor never tends in catching up with the stator field. If it really do so, then there would be no relative speed between the two, hence no rotor EMF and no rotor current, so no torque to maintain rotation. That is what previously I explained. So, the induction motor will always run at the speed lower than the synchronous speed. Hence, the slip will available. Okay. So, end slip. Slip speed is equals to synchronous slip minus the rotor slip. Rotor speed. So, where this is a slip speed, speed of the magnetic field. N sync is the speed of the magnetic field. Nm is the mechanical shaft speed of the motor. That is why the rotor runs at a speed which is always less than the speed of the stator fields. The difference in the speeds depends upon the load on the motor. Okay, the speed differences will be depends upon the load on the motor. The differences between the synchronous speed ns and the actual speed n of the rotor is known as slip. Though it may be expressed in so many revolutions per second, yet it is usually to express it as a percentage of the synchronous speed. Actually, the term slip is descriptive of the way in which the rotor slip backs from synchronism. So, percentage of slip S is equals to ns minus n divided by ns into 100. So, in percentile it is telling, okay. So, ns minus n is called the slip speed. Obviously, rotor speed is n, which is equals to ns into 1 minus s. So, it may be kept in mind that revolving flux is rotating synchronously relative to the stator, that is stationary space, but at the slip relative speed, at slip speed relative to the rotor. So, the rotating flux of the stator is ns, is rotating with ns speed with reference to the stator and rotating with slip speed with reference to the rotor. So, induction motor on no load and on load. See, when the induction motor is on no load, the rotor rotates nearly synchronous speed and the slip will be very small. As the load on the motor increases, the slip speed and the slip increases. Okay. So, it is a general thing. See, if for example, if in a DC motors, when we apply load, what happens? The speed will reduces. Okay. So, here also the same thing. The rotor speed will reduce, hence the slip speed will increase. It means that slip is also increasing. Okay. So, the stator current frequency and the rotor current frequency relations are given in the consequent slides. Okay, it will be given in the link. So here the frequency of the rotor current. When the rotor is at stationary, considering that the rotor is at stationary, the frequency of the rotor current is same as that of the supply frequency. Okay, but when the rotor starts rotating, then the frequency depends upon the relative speed or on slip speed. That is here frequency. The frequency of the rotor is equals to slip times of the supply frequency. What would be the frequency of the rotor's induced voltage at any slip, any speed is this. When the rotor is blocked, that is S is equals to 1. Okay. Rotor is blocked, means it is at stationary. The frequency of the induced voltage is equal to the supply frequency. Okay. On the other hand, if the rotor runs at synchronous speed, we know that the rotor does not run at synchronous speed, but if the rotor runs at synchronous speed, then the frequency will be 0. Okay. So let at any slip speed, the frequency of the rotor current be F dash. Then Ns minus N is equals to 120 F dash by P. Also, Ns is equals to 120 F by P. So we know this, okay? So dividing one by the other, we get F dash by F, which is equals to Ns minus N divided by Ns, which is equals to S. So as seen, rotor currents have a frequency of F dash, which is equals to S times supplied frequency F. And when flowing through the individual phases of rotor winding, give rises to the rotor magnitude fields. These individual rotor magnetic fields produces so here so these individual rotor magnetic fields produces a combined rotating magnetic field whose speed relative to the rotor is 120 F dash P, which is equals to 120 S into the supplied frequency divided by P, which is equals to S into Ns. However, the rotor itself is running at speed N, but the combined rotating magnetic field whose speed relative to rotor is S into Ns. So you have to understand here. So here how the fluxes are rotating with respective to the stator, with respective to the rotor, and with respective to the slip speed. So these everything you need to clearly understand. Okay. So this we will read it again so that you will get clear picture. These individual rotor magnetic field produces a combined rotating magnetic field whose speed relative to rotor is equals to 120 F dash by P. Okay. Here we know even rotor is also having some field. Okay. So which is equals to 120 S into F by P, which is equals to N into S into NS. However, we know but the rotor is rotating at 10 speed. But the rotating magnetic field, the speed with the rotor is, that is also combined rotating magnetic field. Okay. Combined rotating magnetic field with respect to the rotor is S into NS. So, here the 3 points have to remember that. See, these points you may get in ESET. Okay. So, that is why I'm telling you very clearly that, see, once if you understand the concept, there is nothing to bug up or buttify. Okay. So, here the first one is the first point. The rotating magnetic field of the stator with respective to stator is NS. Okay. Second point. Here, combined rotating magnetic field. Yes. We got slip. See, yes, we got slip speed. Okay, that is what it is telling here. The combined rotating magnetic field with respective to the rotor is S into NS. Okay. But here the rotor is rotating at N speed. Here, irrespective of the rotor speed. So these are the points you should be. If you do not understand, you read it twice or thrice, but make understand the concept. Okay. The rotor itself is running at a speed n with the respective to the space. Hence, speed of rotor fields in space is equals to speed of field relative to rotor plus speed of rotor relative to space. So here, the speed of rotor fields in space is equal to the speed of the fields relative to rotor plus speed of the rotor relative to space, which is equals to n into s plus n. which is equals to S into Ns plus N is nothing but Ns into 1 minus S, which is equals to Ns. So the speed of the rotor field in space. Okay. So the speed of the rotor field in space, in air, it is Ns. It means that no matter what the value of slip, the rotor currents and the stator currents each produces a sinusoidally distributed magnetic field of constant magnitude and constant space speed of ns. It is understood that so till here we have covered very important points of an induction motor. Okay. So this is a final point that it is very clearly mentioned that no matter what the value of slip, rotor currents and the stator currents, whatever it might be, but the flux produced is distributed magnetically of a constant magnitude and it will be constant in the space. It will be constant in space speed of ns. Okay. So here, for working of three-phase induction motor, a three-phase revolving flux of constant magnitude and synchronous speed is required. And once again, I will read it. It is understood that for working of three-phase induction motor, a three-phase revolving flux of constant magnitude and the synchronous speed is required. Yes. So there is two requirements, that is a revolving magnetic flux and ns. Okay. Revolving magnetic flux which is rotating at a synchronous speed. And this can be obtained by means of three-phase supply given to the stator three-phase conductors. Further, a rotor torque is set up by using Faraday's laws of magnetism, Fleming's rule and the Lenz's law. Okay. So these are the 3 points very important, that why the rotor is rotating. It does not require any external source or any external motor for rotating the rotor. It by itself it is rotating, hence it is called as a self-starting motor, induction motor. And also we have to note that point that there is no contact between the stator and rotor. It is only by the induction happening. Hence, it is called as an induction motor. So, coming to the quiz. Faraday's law can be used to determine magnitude of induced EMF. Yes. The direction of the induced EMF. No. Both. All of the above. Only the magnitude of an induced EMF. The direction of the induced EMF, what will use? Right hand rule. Okay. Fine. Frequency of rotor currents at standstill. Standstill means the rotor is at constant. It is not rotating. Then you have to remember that. And F dash is equals to S into F. So S will be is equals to 1 at standstill. Then F dash is equals to F. So A is an answer. So these are the frequently asked questions, that is explain the working principle of a three-phase induction motor and what is the slip speed and slip. So thank you. No, before saying thank you, I would like actually show you a video, an animated video which will be more understandable that why a rotor is rotating, why an induction motor rotor is rotating. Okay. So by my explanation also you have got some primary information. Yes, if we see some animation, some videos, we will get a clear picture. So we will see that. So actually, but I want to do one thing because I'm thinking that it's, now I want to step systems. Okay. So the video clipping, the voice is not uh, recording. So I will post this animated video for understanding the working of an induction motor in another post or else for continuation with this video. Okay. Hope you all understood the concept, how the induction motor working and how it is rotating from a standstill position uh, to not to the synchronous speed and less than the synchronous speed. And there is a concept, there is a concept even behind it, why it is not rotating at a synchronous speed. So if you have understood each and every point clearly, if anything you have any doubt, yes, please you can ping me in the comment box. I will get back to you. Thank you so much for listening to me.
Commonly used electrical machines. They are cheaper, rugged, and easier to maintain compared to other alternatives. In this video, we will learn the working of a three-phase squirrel cage induction motor. It has two main parts, stator and rotor. Stator is a stationary part, and rotor is the rotating part. Stator is made by stacking thin-slotted, highly permeable steel laminations inside a steel or cast iron frame. Winding passes through slots of stator. When a three-phase AC current passes through it, something very interesting happens. It produces a rotating magnetic field. To understand this phenomenon much better, consider a simplified three-phase winding with just 3 coils. A wire carrying current produces magnetic field around it. Now, for this special arrangement, magnetic field produced by three-phase AC current will be as shown at a particular instant. With variation in AC current, magnetic field takes a different orientation as shown. From these 3 positions, it's clear that it's like a magnetic field of uniform strength rotating. The speed of rotation of a magnetic field is known as synchronous speed. Assume you're putting a closed conductor inside it. Since the magnetic field is fluctuating, an EMF will be induced in the loop according to Faraday's law. The EMF will produce a current through the loop. So, the situation has become like a current-carrying loop is situated in a magnetic field. This will produce magnetic force in loop, according to Lorentz law. So the loop will start rotating. A similar phenomenon happens inside an induction motor also. Here, instead of a simple loop, something very similar to a squirrel cage is used. Three-phase AC current passing through stator winding produces a rotating magnetic field. So, as in the previous case, current will be induced in bars of squirrel cage, which is shortened by end rings, and will start rotating. That's why it's called an induction motor. Electricity is inducted in the rotor by magnetic induction rather than direct electric connection. To aid such electromagnetic induction, insulated iron core lamina are packed inside the rotor. Such small slices of iron make sure that eddy current losses are minimum. This is another big advantage of a three-phase induction motor. It is inherently self-starting. So, you can see here that both magnetic field and rotor are rotating. But at what speed will the rotor rotate? To obtain this answer, let's consider different cases. Consider a case where the rotor speed is the same as the magnetic field speed. Since both are rotating at the same speed, the rotating loop will always experience constant magnetic field. So, there won't be any induced EMF and current. This means zero force on rotor bars. So, the rotors will gradually slow down. But as it slows down, rotor loops will experience a varying magnetic field. So, induced current and force will rise again. And the rotor will speed up. In short, the rotor will never be able to catch up with the speed of the magnetic field. It rotates at a specific speed, which is slightly less than synchronous speed. The difference between synchronous and rotor speed is known as slip. Rotational mechanical power is transferred through a power shaft. In short, in an induction motor, electrical energy is entered via stator and output from motor. Mechanical rotation is received from rotor. Energy loss during motor operation is dissipated as heat. So, a fan at the other end helps in cooling down the motor. Hope you got a good introduction on the working of induction motors. Thank you.